Alrighty, welcome geometry students. Today we're going to be going over solving right triangles. So we're going to be using trig ratios as well as the Pythagorean theorem to solve right triangles. Alrighty, so let's start our lesson by taking a look at what our trig ratios are. So we've got a right triangle here with sides A, B, and C, and we're going to make theta there our angle. So we're going to take a look at our sides. Side A, that side is opposite of our angle, so I'm just going to label it as such. B is going to be adjacent to our angle, and C, being the side that's opposite the right angle in the triangle, is going to be the hypotenuse. So with trig ratios, if you've got some familiarity with them, you've probably heard of something called SOHCAHTOA. SOHCAHTOA is a quick, neat little way to help us remember some of our trig ratio formulas. So starting with sine is just opposite over hypotenuse. So that would be A over C. Cosine is adjacent over hypotenuse. So the cosine of theta will be B over C. Tangent is opposite over adjacent. So our side A will be over B. A over B is the tangent of theta here. Now we've also got three more special trig ratios from that, first of which is the cosecant of theta. Now the cosecant of theta will just be the hypotenuse over the opposite side. The secant of theta will be the hypotenuse over the adjacent side. The cotangent of theta will be the adjacent side over our opposite side. So those are our 6 trig ratios. Now, you might have noticed that, ignore that notification, with all these, they are basically just the inverse of SOHCAHTOA. Cosecant is the inverse of sine, secant is the inverse of cosine, and cotangent is the inverse of tangent. So if you're ever being asked to find those, you basically just flip sine, cosine, and tangent. So moving on to this first example here, we've got a right triangle with side lengths 3, 4, and 5, and we're being asked to find the 6 trig ratios. So there's our angle theta. I'm going to start by labeling the parts of my triangle. Well, after I write down my SOHCAHTOA to help me remember my trig formulas. Sine, we said, is the opposite over the hypotenuse, which will be 3 over 5. Our cosine, which is our adjacent side over the hypotenuse, is going to be 4 over 5. The tangent of theta, which is the opposite side over the adjacent side, is going to be 3 over 4. So I'm just going to label those parts of my triangle real quick: opposite, adjacent, and hypotenuse. And now we're going to move on to the other 3 trig ratios. For cosecant, I just flip the sign. For secant, I just flip cosine. For cotangent, I just flip the tangent ratio. And that is all 6 of the trig ratios for that triangle. Easy peasy lemon squeezy. So now we're going to move on to the Pythagorean theorem. This you have probably heard before. It is a formula that helps us figure out the sides of a right triangle. So it'll be the square of A plus the square of B, and that'll equal the square of C. So the squares of each of our legs added together is going to equal the square of the hypotenuse. So we've got ourselves a neat little example problem here that utilizes that very concept. So we're going to try to find the missing side of the right triangle, which in our case is the hypotenuse here. So I'm just going to start off by labeling 1/2 being A and rad 3/2 being B. And so our Pythagorean theorem formula, just to refresh, is a squared plus b squared over c squared. Now I'm going to plug in my A value, and I'm going to plug in my B value into the equation. Now I square each of those. So 1/2 squared will be 1/4. Rad 3/2 squared becomes 3/4, and they're going to add up to give c squared. So 1/4 and 3/4 add to make 4/4, which that fraction just simplifies down to 1. Taking the square root on both sides, we get that c is equal to 1, just positive 1. Since lengths are positive, we don't have to worry about the negative case for square roots. Alrighty, so this problem right here, I want you to give it a try on your own. So find the sides of the right triangle when we're given the ratio sine theta being equal to 5/13. Alrighty, so just to backtrack a little bit, the sine of theta we know is the opposite side over the hypotenuse. So we know that the side opposite of theta is 5, and our hypotenuse is 13. So I'm going to go ahead and write those numbers down. Opposite is 5, hypotenuse is 13. We just need to figure out what our adjacent side is. So if, let's say the adjacent side is B. Now I'm just going to take my numbers and plug them straight into the Pythagorean theorem. So 5 squared plus b squared is 13 squared. 5 squared we know is 25, plus b squared is going to equal 13 squared, which is 169. So to solve for b squared, I'm just going to take that 25 and subtract it on both sides to isolate my b squared. So I'm going to go ahead and do that real quick. And I'm going to get that b squared is going to equal 144. Then I'm going to take the square root of both sides there, and I'll get that b equals 12. So that is our third and final side. Alrighty. So next up, we've got ourselves quite an interesting example. This one I want you to think of as an extension problem. So we've got ourselves a right triangle here, and we're given that the tangent for that right triangle is 1. So when in doubt, draw it out. So we're going to start by drawing ourselves a right triangle. There's our right angle. And let's say the angle theta is right there. So we know that the tangent of theta is equal to 1. Now we know that the tangent is equal to the opposite side over the adjacent side, and that's equal to 1. So that means our opposite side has to be equal to our adjacent side. And so those two sides have to be equal in length. And so that is an isosceles triangle, specifically an isosceles right triangle. Alrighty, that concludes our video lesson for today. If you have any questions, please bring them into class, and we will be going over them. We'll also be going further in depth into using Pythagorean theorem more, as well as trig ratios. Have a good day, good afternoon, or good evening, wherever you might be. See you tomorrow.